Okay, welcome to lecture 34. We're still on unit 5 here, plane autonomous systems. And so in the previous class we introduced the types of critical points and we classified those types of critical points according to their behavior. Okay, so mostly we did this through drawing images of the critical points. But today we're going to move on to classifying the critical points mathematically, and in this class we're going to focus on linear systems. In a future class we will look at non-linear systems, but today we're just focusing on linear systems, critical points and their stability. So recall, a critical point is a point where both of the ODEs in the system are simultaneously equal to 0. So dx by dt equals 0 and dy by dt equals 0. Okay, so they have to be equal to 0 simultaneously. If one is equal to 0 but the other is not, then we do not have a critical point of the system. Okay, and also recall we wrote this system as in matrix form. So we took the system of two linear first order ODEs and wrote it in matrix form, and we showed last time that the only critical point for these linear systems is the origin, the point 0, 0. Okay, and this is basically the last slide from last class, that the eigenvalues of this matrix A are given by, if tau is the trace of the matrix A and capital delta is the determinant of the matrix A, the eigenvalues of this matrix A are the trace plus or minus the square root of the trace squared minus 4 times the determinant over 2. Okay, and we said that the eigenvalues of this critical point at 0, 0 can either be real, unique and of the same size, real and equal, or in other words repeated eigenvalues, real and of the opposite sign. They can be complex conjugates, or they can be complex conjugates with 0 real part, or in other words, pure imaginary. And so each of these 5 cases here is going to give us different behavior of that critical point, and different stability also of the critical point. Okay, so let's look at these 5 cases here. So case 1, 0, 0, the critical point at 0, 0 for this linear system is a node if lambda 1 and lambda 2 are real, are not equal to each other, but they are of the same size. Okay. So we have a node at the critical point 0, 0 if lambda 1 and lambda 2 are real, unequal and of the same size. Additionally, we can talk about the stability of this node. So this node is asymptotically stable if both lambda 1 and lambda 2 are negative, and unstable if both lambda 1 and lambda 2 are positive. So let's recall what a node looks like again. So a node is a critical point where all of the trajectories are either pointing towards that critical point, such as in the first 2 cases here, or thirdly, if all the trajectories nearby that node, nearby that critical point, are pointing away from the critical point. Okay, so these are 3 examples of nodes here. So you might say this first, these first 2 examples are asymptotically stable, because as time continues on and gets larger and goes to infinity, these trajectories move towards the critical point. And the third example here, okay, well this would be an unstable node because the trajectories are moving away, right? Okay, so the sign of the eigenvalues determines which case we're in here, whether we're in an asymptotically stable node or an unstable node. Okay, so let's just look at the proof really quickly. So lambda 1 is not equal to lambda 2, but they are both real, okay? Okay, so there are a few subcases we need to look at here. The first one we'll look at is the negative case. So remember, we are looking at lambda 1, lambda 2 being real, unequal, and of the same sign. So this is why in the first subcase here, we're looking at the case where lambda 1 and lambda 2 are both negative. Okay, well, the general solution to this case, if you remember from Unit 4, is x of t equals c1 times the first eigenvector associated with the eigenvalue lambda 1 plus c2 times k2 e to the lambda 2t, where k2 is the eigenvector associated with lambda 2. So remember, if we have distinct real eigenvalues, we can always find a linearly independent set of eigenvectors. So here we've got k1 and k2. Okay, so this is the general solution in the negative in this case here. So let's assume for a minute that c1 is not equal to 0 and c2 is equal to 0. So this second term here we can ignore for now. What's happening to this first term here if c1 is non-zero? Okay, well, because lambda 1 is negative, as t goes to infinity, this exponential of something negative times t, well, this exponential goes to negative infinity. So we get e to the negative infinity, which is 0, of course. So the exponential of negative, the limit as the exponential goes towards e to the negative infinity is 0. Okay, so in the first case here, the general solution approaches the 0 vector, or the 0 point, the critical point. In the opposite case, where c1 is 0 and c2 is not, well, the same thing happens, right? Because if c1 is 0, this term is 0. The second term here, lambda 2 is still negative, so that exponential is going to 0 as t goes to infinity. So, in fact, we approach the same critical point 0, 0 as t goes to infinity. In general, if we look at the case where the lambda 1 and lambda 2 are still both negative, but lambda 2 is smaller than lambda 1, then we can actually extract out this term e to the lambda 1t from the general solution. Okay, so we can write the general solution on the left here in the form on the right here, just by extracting out this term e to the lambda 1 times t. And well, if you multiply the brackets here, the square brackets, by this e to the lambda 1t, you'll find the general solution. So feel free to convince yourself of that. But this term on the right, the most far right term here, this term is negligible compared to c1 because lambda 2 minus lambda 1 is less than 0. Okay, so this term is really quite small compared to the other term here. Okay. And in the end, basically the same thing happens. As t goes to infinity, the general solution approaches the critical point. So in the case that both eigenvalues are real, unequal, and of the same sign, we have a node. And in the negative case, where they're both the same sign and negative, we always approach that critical point 0, 0. Okay, and you can make the same argument actually if lambda 1 is less than lambda 2, in fact. That we always approach the critical point as t goes to infinity. Okay, so key point is lambda 1, lambda 2 are real, unequal, and negative. Then we have a asymptotically stable node. However, if they're both positive, so if our eigenvalues are both positive now, then we have an unstable node. Okay. So the trajectories have the same pattern as in the negative case, but if you look at the general solution here, if lambda 1 and lambda 2 are positive, then these exponential terms are going to go to infinity as t goes to infinity, because we have the exponential of some positive number which is going to infinity, and of course we know that the exponential function goes to infinity as t goes to infinity. Okay, so the reason that this node is unstable if lambda 1 and lambda 2 are positive is that both of these terms are diverging as t goes to infinity. Okay, so we don't move towards the critical point in this case. The node is known as unstable. Okay, I'll give you a summary slide of all these cases at the end of this lecture. But for now, let's move on to case 2. The critical point 0, 0 is a node if lambda 1 equals lambda 2. So now we have a real eigen, two real eigenvalues, but it's repeated. So we have in fact, maybe you would say a single eigenvalue of multiplicity 2. Okay. So it turns out that if these two are equal, these two eigenvalues are equal, then we have a node again. And we say the origin or the critical point is stable if lambda is negative and unstable if lambda is positive. And again, this is the same as in case 1, where if the eigenvalues were negative, we had asymptotically stable, and when they were positive, we had unstable. Okay. So again, just a reminder of what a node looks like. Let's have a look at the proof. So if lambda 1 equals lambda 2, then we know that the general solution can be written like so. Well, in fact, so if we can find two linearly independent eigenvectors, then the general solution is given at like so. So notice here the difference from last time, from case 1, is in the exponential terms, e to the lambda 1t, e to the lambda 1t. The eigenvalues here, or the coefficients in the exponential, are equal in this case because we only have one eigenvalue, right? Because it's repeated. So in the case that we can find two linearly independent eigenvectors, then this is the general solution. Okay, and I can pull out the exponential term and write it like so. So if lambda is less than 1, then of course it's pretty clear that x of t is going to go to 0 as t goes to infinity, because lambda 1, e to the lambda 1t, if lambda 1 is negative, this is going to 0. This exponential term is going to 0. Okay, but we can say a little bit more about this. So if lambda 1 is less than 0, then the general solution goes to 0 along the line determined by a vector in this bracket here. Okay, so whatever direction that this is pointing in, this line here. So we've got two vectors, right? We're basically just summing two vectors with some scaling constants here, c1 and c2. So the sum of these two vectors gives us a direction, and we're saying that if we start on that line, we move towards the critical point at the origin along that line. Okay, and we call the critical point a degenerate stable node in this case. Degenerate because the eigenvalues are repeated. If lambda 1 is greater than 0, then of course this term is going to be exponential of lambda 1 times t. If lambda 1 is greater than 0, as t goes to infinity, this is going to be diverging to infinity, right, as t goes to infinity. So the general solution, or x of t, is going to be going to infinity as t goes to infinity. We still move along this line, along this line here, but the arrows on the trajectories are reversed, and we have a degenerate unstable node. Again, the degenerate word just comes from the fact that we have repeated eigenvalues. Okay, but remember in the case that in Unit 4 we were solving where we had repeated eigenvalues, we could find two linearly independent eigenvectors, but sometimes we couldn't. So if we had a single linearly independent eigenvector, then the general solution was given like so. Okay. Okay. Well, previously in Unit 4, I was calling this vector p. I was calling it k2. Okay, but basically, if you recall, we had to solve the eigenvalue equation a minus lambda I times k1 equals the 0 vector, and that's how we got the first eigenvector. And then we had to solve, in this case, if we're calling it p, we had to solve the a minus lambda I times p equals k1. So if you don't remember this, go back to Unit 4 material and how we solve a system of equations where we have a repeated eigenvalue in the coefficient matrix A and only one linearly independent eigenvector. Okay, well I did write this down. Good. Okay, so well, I can pull out a common factor of t times e to the lambda 1t out of this equation, right? So just pulling out that term, then of course I end up with a 1 over t in two of these terms. So in this first term here, and in the p term here. So if lambda 1 is less than 0, the limit as t goes to infinity of t times e to the lambda 1 times t is going to be 0. And that's because, of course, an exponential decays much faster than a polynomial. So we've got a polynomial t times an exponential here. So if lambda 1 is less than 0, the limit as t goes to infinity is 0. And x approaches the origin or the critical point. The critical point is at the origin. And one of the directions determined by k1. Okay, so the critical point is again called a degenerate stable node. Stable because it is approaching the origin, which is the critical point. But of course, for lambda 1 greater than 0, then both of these terms, t is going to infinity as t goes to infinity. An exponential of something positive times t is going to infinity. So for lambda 1 greater than 0, then this thing diverges to infinity, and we get a degenerate unstable node. So the key point here is that if we have repeated eigenvalues, the critical point at the origin is stable if lambda is less than 0, so if the eigenvalue is less than 0 or negative, and unstable if lambda is greater than 0. And if we have a repeated eigenvalue, we add this word degenerate in front of the stable node and unstable node. So degenerate stable, degenerate unstable node. Okay, well, case 3, the critical point at the origin is an unstable saddle point if lambda 1 and lambda 2 are real, but of the opposite sign. So one of them is positive and one of them is negative. And so remember what an unstable saddle point looks like. Well, we have two lines that are moving away from this critical point at the origin here along the green line. So they're unstable along the green line, but it's stable along this red line, right? So we're moving towards the critical point along the red line. So we call this an unstable saddle point. And so if we have two real eigenvalues but of opposite signs, so they're obviously distinct, they're not equal to one another. So the general solution is just, again, given like so, where lambda 1 is of opposite sign to lambda 2. If lambda 1 is greater than 0, lambda 2 and less than 0, then the positive exponential e to the lambda 1t is the dominant term for large T, because the other term goes to 0. The exponential of something negative times t goes to 0 as t goes to infinity. And so what this says is that this first term is what's dominating at large time, and all trajectories are asymptotic to the line through k1. So this vector, that direction k1. And of course, if the opposite is true, then we just switch, right? If lambda 1 is negative and lambda 2 is positive, this term is basically going to 0 as t goes to infinity, and the general solution is dominated by this term, which is going to infinity, and all trajectories are going to end up moving along this line c2 times k2. Okay, so that one's not too hard. Case 4 is where we have some complex eigenvalues. So 0, 0, the critical point, is called a spiral point if lambda 1 equals alpha plus I times beta, where alpha and beta are the real part. Alpha is the real part of lambda 1, and beta is the imaginary part. The second eigenvalue, of course, is the complex conjugate. A significant thing to note here is that alpha is not equal to 0. Okay, spiral points have a real part to the eigenvalues. So alpha is not 0 here. So the origin is stable if alpha is negative and unstable if alpha is positive. So let's just, if alpha is negative, then we have these kind of spiral points where we're spiraling in towards the center, kind of like being sucked in by a black hole. And if alpha is positive, then we just get repelled by this center, this critical point here, and we spiral away from this critical point. Okay, so the proof, of course, is that, well, if we have complex conjugate eigenvalues, then we have these two real solutions here. Again, this is from Unit 4. So I can write down the solutions in terms of x and y. So we have e to the alpha t times some constant times cosine plus some constants times sine. Remember that cosine and sine are both, they can never be larger than 1 or less than 1. So this term in bracket here are bounded by -1 and 1. Well, okay, by some, we've got some constants in front of them here, so I guess you would say by plus or minus the constants. But these constants are finite, right? So they're never going to infinity. So really what the long-term behavior as t goes to infinity is determined by is the exponential terms out front. So if alpha is less than 0, then both x and y are going to 0 as t goes to infinity, because if alpha is negative, this exponential is going to e to the negative infinity, which is 0. Okay, of course then if alpha is positive, then this exponential diverges as t goes to infinity, and both x and y approach infinity as t goes to infinity. So we have this alpha less than 0, our spiral point is stable, because we approach the critical point. But if alpha is positive, this exponentials diverge and we have an unstable spiral point. And finally, the critical point 0, 0 is called a center if we have complex conjugate eigenvalues with 0 real part. Okay, so alpha is 0 here. This is the key point. We have no real part in our eigenvalues. Our eigenvalues are pure imaginary. Okay. All solutions are periodic with a period 2 pi over beta. So remember, this is what a center looks like. And again, the proof is pretty straightforward. We have real solutions of this form, same as before, but now alpha is 0. So we just we don't have that exponential term, in fact. Okay, so then if C12, which is the sine term here, and C21, which is the cosine term here, are equal to 0, then we have these solutions here, which is a standard parametric representation of an ellipse, right? I can add these two together. Well, in fact, I can square these two terms, so x squared, y squared, and add them together. On the left-hand side, I'll get x squared plus y squared. On the right-hand side, I'll have some c11 squared cosine squared plus c22 squared sine squared. And I could have factored out the C11 and the C22 out before I square it, actually. And then on the right hand side I'll have cosine squared plus sine squared, which is equal to 1. And so you recognize this as the equation of an ellipse. And so in general, for C12 not equal to 0, and similarly for C21, you can also show that all of these solutions are ellipses as well. Okay, so we went through a lot of cases there, and really what I really would like you to know is this summary slide here. So this might be a slide that you like to add to your favorites or something, or send to a friend and say, oh look, this is great, read this slide. Or really maybe you just want to print it out. And this is really the summary of how we classify critical points of linear systems. Okay, so we've got this linear system here. We can calculate its trace and its determinant, and we can write down the two eigenvalues based on the trace and the determinant of this matrix A. Case 1, we have a node, and of course it's asymptotically stable if lambda 1 and lambda 2 are both negative, and unstable if they're both positive. We have a node if we have a repeated eigenvalue, stable if the eigenvalue is negative, unstable if positive. An unstable saddle point if lambda 1 and lambda 2 are real but of opposite sign. A spiral point if we have a complex conjugate eigenvalues with non-zero real part. And again, stable if the real part is negative, unstable if the real part is positive. And we have a center if we have a complex conjugate eigenvalues with zero real part. So pure complex eigenvalues. So print out this summary slide because we're going to be referring to it as we move through examples. Speaking of which, classify the critical points of the following plane autonomous linear system. Well, it's a linear system, so I don't know why I said points, because we only have one. We only have the origin. So we're going to write this system in matrix form, which we should be familiar with by now. We can immediately read off the coefficient matrix A. We have 5, 3, -4, -3. If I calculate the trace of this matrix, I have 5 plus minus 3, so 5 minus 3 is 2. If I calculate the determinant, 5 times negative 3, take away negative 4 times 3, so I believe that's negative 3. Okay. Therefore, the first point is the determinant is non-zero, so 0, 0 is the only critical point. We're not looking at a line of critical points. I can write down the eigenvalues to my system, so the trace plus or minus square of the trace minus 4 times determinant divided by 2. Okay, and if I put these two calculations into my calculator, I get two real distinct eigenvalues of opposite sign. Okay, and if you remember, if we go back to our summary slide, real distinct eigenvalues of opposite sign is case 3. So we have an unstable saddle point here because lambda 1 and lambda 2 are real, but they're of opposite sign. So we have an unstable saddle point. Okay, well, example 2, again, we're going to just do the same thing here. Write down the coefficient matrix A, writing the system in matrix form. I'm going to calculate the determinant, the trace first. 1 plus negative 3 is negative 2. The determinant 1 times negative 3, take away negative 5 times 1 is 2, which is non-zero, so we're okay. We've got a single critical point at the origin. We can calculate the two eigenvalues here, and it turns out that we have complex conjugate eigenvalues with real part equal to negative 1. Okay, so we have a non-zero real part. The real part is negative, so alpha is negative. So if I come back to my summary slide, case 4, we have a spiral point because we have complex conjugate eigenvalues with non-zero real part, and it's in fact the origin, or the critical point at the origin, is stable because alpha is negative. So therefore 0, 0, our critical point at 0, 0, is a stable spiral point. Okay. And so again, this is just a reminder that, recall that, we can remember this formula here if we like, or we can, for a two-dimensional system, or we can recall that for a two-dimensional system, sometimes it's easier just to remember that the sum of the eigenvalues is the trace of the matrix, the product of the eigenvalues is the determinant of the matrix. So in the next class, we're going to be moving on to nonlinear systems, and we're going to be trying to see if we can classify critical points of nonlinear systems in the same way. So for nonlinear systems, we're going to get critical points that are not at the origin. Nonlinear systems, we can get critical points that are away from the origin. So we're going to see how that affects our results. Okay, thank you. I'll see you there.